Good day, everyone. I am Samuel Jr. A. Pinales, the last reporter of Group 3 who were assigned to talk about the path line. So, some of my group mates have already discussed their topics about pathline, which are the definition, meaning, and other relevant informations about it. So, for my topic, I will be more focused on discussing the motion of many particles in a fluid. So, to start, for a fluid motion, there are infinitely many fluid particles that we could choose to follow. So, there will be infinitely many path lines. This means that in every fluid particles you are following, you will have the same amount or the same number of path lines. So, example, if you are following 3 or 5 or let's say 5 particles, then you will have a 5 path lines since those 5 particles will make their 5 path lines or will make path lines as they move or travel from one position to another. So, what is or what does a path line looks like? So this is an example of a path line. So we have a point Q, there's a line and an arrow. So this line is what we call the path line. Then the fluid particle is traveling through point Q in the is traveling through this line towards point Q. So this arrow here indicates that the position or the direction of the fluid particle is going up there. Suppose that we take one particular fluid particle that travel along a path through the point Q. So here it is shown here that this is the one particle that we have chosen to follow, wherein it travels along the path of the point Q. If the position vector of the fluid particle when at Q or at point Q is r, then its velocity is given in terms of r by the equation the velocity is equals to the rate of change of the position, or the velocity is equals to dr over dt. So next, the velocity of the fluid particle when at Q is the same as the velocity vector field or u of the fluid at Q. So, the velocity of the fluid particle when at Q and the velocity vector field of the fluid at Q is the same. So, since the velocity is equals to the rate of change of the position, then the velocity vector field or the u is has also the same equation, wherein it has the change of the the rate of the change of the position is equals to the velocity vector field. So in order or in realization, um, the v is equals to dr over dt, or the rate of the change of the position is equals to u, or the velocity vector field. So those two were the same. In general, the velocity vector field depends on position and time. So, same sa velocity, nagdepend siya sa position and time, wherein the r there indicates the position and the t from below indicates the time. So, that is the vector equation represents coupled scalar differential equations, wherein it links the x and y coordinates or axes and the t, which means time. So to proceed, we have an example here wherein we're going to find the equations of the path lines of for a fluid flow with velocity field. We will be using the velocity vector field. So u, or the velocity vector field, is equals to the a constant of y times I plus b constant of time times j, where a and b are both positive constants. So I know that you already know what does the constant mean, wherein it cannot be changed. So to proceed, sketch the path lines of the fluid particles which pass through the points x and 0 at time of is equals to 0 for x is equals to -1, 0, 1, 2, and 3. So, since we have these five, what do you call that? Since we have these five that indicates the position of x, which is -1, 0, 1, 2, 3, the coordinates, then we will be also having five path lines. Let's say that these are the we are going to follow five fluid particles, so we will be having five path lines in this example by using these given numbers. So for the solution, the vector differential equation 1.3 for the path line denotes or gives the rate of change of the position is equals to the velocity vector the rate of the change of the time is equals to the velocity vector is equal, and the velocity vector or u is equals to the a constant of the y coordinate times I and the b constant of the time and j. So by the definition, this given equation will be defined into the dr over dt, or also read as the rate of change of the position is equals to the dx over dt, or the x coordinate over the time, times I is equals to the dy over dt, or the y coordinate over the time is multiplied to j. And to further to further give or to further explain or to further break down this equation, the dx over dt, where a is constant and the y is the coordinate or the axis, and on the other hand the dy over dt is the is equals to b, the constant, times the t, which represents time. So the second equation integrates to give the second equation here is the dy is over dt is equals to b times the time. So the second equation integrates to give the y is equals to 1/2 of b constant t squared or time squared plus c, where c is an arbitrary constant. Then on the other hand, from the first equation, we will be having the dx over t, or the x coordinate over time, is equals to the a constant of the y coordinate is equals to the 1/2 b constant times the time squared plus a of the constant c. This integrates to give an x is equals to 1/6 of the ab constant times the time cube plus a constant of the c arbitrary constant times t, or the time, plus d, which is also an arbitrary constant. So to proceed, these equations for x and y in terms of time represents infinitely many curves in the region of fluid. So it was already seen, or it was already given that that these terms of x and y in terms of the time will be representing an infinitely many curves. So we will be having many curves in this um, activity or this example by using that x and y terms, wherein it gives wherein it was um, in terms of the time. For each pair of values of c, which is the arbitrary constant, and the d arbitrary constant, we obtain a different path line. So because of this two arbitrary constant, we obtain a different path lines depending on the fluid particle we choose to follow. The path line of the particle which passes through the point x of 0 at time with a 0 and must be such that x is equals to main x and y is equals to 0, wherein at t is equals to 0 or the time is equals to 0. So that gives us the y of 0 is equals to the arbitrary constant c is equals to 0 as well, and wherein x of 0 is equals to the arbitrary constant d is equals to x. So the equation here answered that must be or through the point x of 0 or and 0 at time of 0. So we must achieve the x is equals to x and wherein y is equals to 0 at the time at with 0 time. So this equation shows wherein the y of 0 or the time of 0 is equals to the arbitrary c, wherein the arbitrary c is equals to 0. So that indicates that y here is equals to 0, which is correct. Then the next one is x of the time 0 is equals to the d arbitrary constant is equals to x. So that indicates that x here is equals to x or big X. So to continue, we now have x is equals to x in relation of its time, and y is equals to y in relation of its own time. With time as a parameter, we can, in principle, eliminate time to obtain the equation relating directly of y directly to x. This is done for the specific case above. So this equation above is we have already cancel or eliminate that time here. So for us to directly relate the y-axis or the y-coordinate of into the x-axis, so that's why we have the x is equals to x and y is equals to 0. To proceed, the path line equations for this article are then we will be having another equation here. I'm so sorry for the background noise. So here we have the equation x is equals to 1/6 of AB constant multiplied by the t or the time cube plus the x, and also the coordinate of y is equals to 1/2 of b constant times the time squared. These equations define the path line for any specified time interval. So those two equations will help us or will be the one to define the path line for any specified time interval. So in any time, these two will be the one will be both will be the two we're going to use. So we can eliminate the parameter or the time. So we are going to eliminate the parameter time from these two equations to obtain an explicit equation for the path line, wherein we'll be having a close parenthesis of x minus the big X, close parenthesis, raised to the power of 2, wherein it is equal to the 2a squared over 9b multiplied by y cubed. So that equation given there help us to locate and give us the path lines that we are looking for. So the path line corresponding to x is equals to negative 1, 0, 1, 2, and 3 are shown in the figure below. So in which, for convenience, we have taken the b over a squared is equals to 16 over 9. So the graph shows 5 path lines wherein we are in different nga given sa x, or given kang position sa x, which is negative 1, 0, 1, and 2, and 3. So we can see here that the Q1 have crossed the line of the negative 1, or the x have crossed the line of the x. The Q1 R1 have crossed the line of the x and 2. So there are 5 path lines here, which wherein we have followed 5 fluid particles also. So to further discuss and give more information, with the b over a squared is equals to 16 over 9, the path line Q1 R1 crosses the y-axis at y is equals to 2. As you can see, at y is equals to 2, so that 0, 2 there, it is where our Q1 R1 crosses at y-axis. By using this equation b over a squared is equals to 16 over 9. So as indicated, more general, c crosses the y-axis at y is equals to 9b over 2a squared multiplied by 1/3. The direction of flow, shown by arrowheads, which is upward, can be deduced from the sign of either component of the u or the velocity vector, so for example, the u term 1 is equals to a constant of the y-axis is positive in the upper half plane, where y is greater than 0, so the flow is from left to right. So if the y is greater than 0, the flow will be from left to right. Then only the flow for the time is greater than or equal to 0 is shown here. So ang kaning sa graph nga gipakita diri, ang iyahang flow is ang naka-relate siya sa time, wherein ang sa time is greater than or equal to 0 ang iyahang kuan. So kung equal to 0, nagikan siya sa left. And if ang y imuha is only dapat greater than 0 ang iyahang y para magikan siya sa left ang iyahang flow up to padung adto sa right. So note guys that the particle which travels along the path line of Q1 R1, for example, was at the point of Q1 when the time is equals to 0. Note that the same scale should be used for the x and y axis, since we wish that path lines to be visual representation of the real flow. So that's all about my report, and I hope you guys have learned something. So yeah, thank you so much for listening, and thank you.